Hello, my name is Stephanie Lechke, and today I'm presenting my work on the end Permian mass extinction and relative ecological changes between herbivorous and carnivorous synapsids. To begin, mass extinctions are few and far between when compared to the enormity of geologic time, but it can be argued that these pulses of planetary upheaval have radically controlled and shaped the biota of Earth, ultimately leading to the plethora of body plans, life modes, and ecological diversity seen today. This is possible through the selectivity of mass extinctions, both in those genera that go extinct and those that originate after such an event. It is the non-random nature of extinction events, where the abundance, species richness, geographic distribution, and intrinsic biotic characters of a particular genera dictate its success in either surviving dramatic ecological disturbances or originating in an entirely new ecosystem. It is the intrinsic biotic characters that are of a particular interest to me. For context, here is a graph by Benton displaying the number of terrestrial families through time. And important to note is the drop in diversity seen at the Permian-Triassic boundary, where over 70% of terrestrial genera went extinct. Synapsids were the dominant terrestrial vertebrate fauna from the Pennsylvanian until the Triassic. The earliest synapsids, the pelycosaurs, appeared during the early Pennsylvanian period. During the Middle and Late Permian, most pelycosaurs either went extinct or evolved into the therapsids. Very few therapsids survived into the Triassic, but the ones that did include the therocephalians, dicynodonts, and cynodonts. It is believed that the first true mammal, Morganucodon, appeared at the end of the Triassic. This work will build upon previous studies of synapsids across the Permian-Triassic interval. Huttenlocher analyzed the impact of the Pt extinction on the distribution of body sizes in non-mammalian eutheriodont therapsids. Looking at his plot of basal skull length against time, it is evident that therapsids as a whole experienced a decrease in size across the extinction interval. Therapsids are a subset of synapsids that excludes more basal members of the group. Angelzig and Roopnarine modeled the impact of primary productivity loss on synapsids during the Pt extinction event at the community level. The authors defined secondary extinction as the extinction of a species owing to the elimination of dependencies on at least one other species within the community. The lower axis of the plot represents units of primary productivity lost, while the y-axis is secondary extinction rate within the guild. Plot A, as seen here, represents a guild composed of small herbivores. Higher levels of secondary extinction are restricted to productivity loss of about 1,000 units. Now plot B, which is modeling large carnivores, shows that carnivores experienced higher secondary extinction rates at lower levels of primary productivity loss. This shows an increased sensitivity of carnivores to said primary productivity loss, which was prevalent and geographically widespread during the Pt extinction. So my question now becomes, what was the role of the Permian-Triassic extinction event and recovery in changing the relationships between body size and diet in synapsids? To complement this, was selectivity more critical in driving patterns of survivorship and extinction, or in determining how ecological structure rebounds through origination? In order to answer this question, I used the literature, as well as two papers by Huttenlocher and Sukius, to compile a list of 313 genera that had both a skull length and diet attributed to them. Of the total genera, 149, or roughly 47%, were herbivores. 164, or 52%, were carnivores. This is including the low number of genera designated as omnivores and insectivores. First and last appearance dates were downloaded from the Paleobiology database. And using multivariate statistics in RStudio, I first measured the impact of extinction selectivity in driving patterns of survival and extinction with regards to body size and diet. To complement this, I measured origination selectivity to understand the impact of recovery periods. Logistic regression is an effective way to measure extinction and origination selectivity, in that it uses the binary outcomes of extinct or survive to quantify the impact of multiple simultaneous predictors. Here is an equation that I used, in which extinction is predicted by body size and diet. In this scenario, the diet character is a binary variable, while the log transformed skull length is a continuous variable. The same was done to measure origination. In order to keep my sample size as large as possible, a proxy had to be used for body size. In my case, I chose skull length. This is a commonly used proxy that tends to be a good representation of body mass in both mammals and reptiles, as seen in work done by Fitch. When comparing log mass of mammals to their skull length, face length, and palate length, a clear correlation occurs. In addition, not only are cranial elements preserved more readily than postcranial material, but skull length in synapsids is found to have correlated linearly with femur length, another commonly used proxy for body mass. Here's a distribution of the synapsid diversity of my dataset from the middle Permian through the end of the Triassic. Herbivore diversity is represented by the blue line, and carnivore diversity is represented by the red line. The x-axis is geologic time, while the y-axis shows the number of genera. The purple line, as in all subsequent plots, denotes the PT boundary. It can be seen that synapsids achieved their greatest richness in genera during the middle and late Permian and suffered a dramatic reduction in diversity as a result of the extinction event. When plotting mean skull sizes through time in herbivores as compared to carnivores, it can be seen that their body sizes mirrored each other in trajectory and magnitude prior to the PT extinction. At the PT boundary, there was a sharp decline in the average size of both carnivores and herbivores. This potentially looks like the so-called Lilliput effect, the phenomena of a temporary decrease in the size of fauna in response to an extinction event. During the Triassic recovery, both experienced a rapid increase in body size, with carnivores consistently smaller than herbivores by a factor of about 1.8. This sustained separation of herbivores and carnivores in mean body size is reminiscent of modern mammalian ecosystems, a trend displayed by the fauna of the African savanna. Now onto our selectivity analysis. When looking at the logistic regression plots measuring body size selectivity, points placed in the upper region of the graph, above the zero axis, show a preference for the extinction or origination of larger taxa, while the lower half of the plot indicates selectivity towards smaller taxa. As can be seen here, there is no strong preference for extinction selectivity with regards to body size during the PT interval. All we see is a sustained slight decline beginning in the Capitanian and ending in the Anisian. When looking at the logistic regression plots measuring diet selectivity, points placed in the upper region of the graph, above the zero axis, show a preference for the extinction or origination of carnivores, while the lower half of the plot indicates selectivity towards herbivorous taxa. Analyzing the log odds of extinction with regard to diet type, we see most points hover around the zero line. This once again shows that there was no strong extinction selectivity with regard to diet, as herbivores and carnivores at the PT boundary had an equal probability of going extinct. Interestingly, when looking at origination selectivity with regards to body size, it can be seen that immediately post-Permian Triassic extinction event, there was a strong tendency for smaller taxa to originate regardless of diet, although this was a temporary pulse. This trend is actually mirrored in mean synapsid skull sizes through time. If we recall, there was a significant drop in the size of genera, but a quick recovery by both herbivores and carnivores. These data show that the shrinking body sizes may have been due to origination of smaller taxa rather than the selective extinction of larger bodied organisms. Finally, when looking at origination with regards to diet, we see no strong selectivity around the PT boundary. What we do see is a pulse of selection for new herbivorous genera to evolve in the Ladinian during the Middle Triassic. Once again, this is temporary, as during the Carnian, selectivity returns to previous values. In conclusion, this work exhibits the ability of mass extinctions to disrupt size distribution of herbivores and carnivores, which impacts ecosystem function. The lack of extinction selectivity during the PT extinction, followed by origination selectivity, highlights the importance of recovery intervals in determining how ecological structure rebounds after mass extinction events. And with that last thought, thank you for your time and thank you so much for watching.